Imagine standing on the rusty, wind-swept plains of Mars, peering out at a landscape that once flowed with water, holding the secrets of an ancient era. Mars, the red planet, has long fascinated humanity, and its enigmatic history of water has captivated scientists and explorers alike. Join us on a journey to uncover the mysteries of where did the water on Mars go, as we delve into the parched Martian deserts and unlock the watery secrets that could shape the future of space exploration. Mars, our enigmatic neighbor in the solar system, has long captured human imagination and curiosity. Often referred to as the red planet, its surface today presents a cold, barren, and dry landscape. However, abundant evidence suggests that this was not always the case. There was a time, billions of years ago, when Mars possibly boasted extensive water bodies, rivers, lakes, and perhaps even oceans. This introductory section delves into the compelling mystery of Mars's past, a time when it was potentially more Earth-like, with an environment that might have supported life. Geological features observed by various Mars missions have painted a picture of a planet that once had conditions suitable for water in its liquid form. Features such as dried-up river valleys, delta formations, and mineral deposits that only form in the presence of water strongly indicate that Mars was once home to significant amounts of water. This section will explore the evidence gathered from missions like NASA's Mars Reconnaissance Orbiter and the Mars Rovers, which offer tantalizing clues about the planet's watery history. What we see today is a stark contrast to this wet past. Mars now is a world with a thin atmosphere, where liquid water cannot exist on the surface for extended periods. This part of the introduction will briefly touch upon the major turning point in Mars's history, the transition from a warm, wet planet to the cold, arid one we observe today. Theories suggest this dramatic change involves the loss of its magnetic field, atmospheric thinning, and a significant climatic shift. Understanding where the water went is not just a matter of solving an intriguing planetary mystery. It has significant implications for our understanding of habitability and the potential for life on other planets. This introduction will set up the quest to uncover the fate of Mars's water as a vital piece in the puzzle of understanding the planet's past, present, and future. It also holds the key to understanding the processes that can change a planet's climate and habitability over time. This exploration will raise several questions. How did Mars lose its water? What were the processes involved? Could some of this water still be present, locked up in ice or underground reservoirs? And most intriguingly, what does Mars's history tell us about the potential for life, past or present, on the red planet? These questions are not only of scientific interest, but also stir a sense of wonder about the universe we live in and our place within it. As we embark on this journey through time and space, the introduction will set the tone for a deep dive into the scientific discoveries, theories, and ongoing research that aim to unravel the mystery of Mars's disappearing water. From the ancient past to the present and looking towards future missions and research, this script will aim to provide a comprehensive overview of one of the most fascinating questions in planetary science. Mars, the fourth planet from the Sun, is a world of extremes and contrasts. Often called the red planet due to its reddish appearance, which is caused by iron oxide, rust, on its surface, Mars is a planet with striking features. This section will delve into the physical characteristics of Mars, including its size, mass, and composition. Mars is about half the size of Earth, with a diameter of 6,779 kilometers, and it has a thin atmosphere composed primarily of carbon dioxide, with traces of nitrogen and argon. Mars boasts a diverse landscape, marked by the largest volcano and the deepest, longest canyon in our solar system. Olympus Mons, a shield volcano, is about 22 kilometers high and more than 600 kilometers in diameter. Valles Marineris, the Grand Canyon of Mars, spans over 4,000 kilometers in length and reaches depths of up to 7 kilometers. This section will explore the diverse geological features of Mars, including its polar ice caps, which are made up of water and dry ice, frozen carbon dioxide, and the evidence of ancient river valleys and lake beds. Mars experiences a wide range of climatic conditions, largely due to its thin atmosphere and axial tilt. The Martian climate is characterized by significant temperature fluctuations, with temperatures that can vary from -125 degrees Celsius during winter at the poles to 20 degrees Celsius at midday near the equator. This part of the overview will discuss the climatic conditions of Mars, including its seasons, weather patterns, and the infamous Martian dust storms that can envelop the entire planet. The orbit and rotation of Mars have a significant impact on its environment. Mars takes about 687 Earth days to orbit the Sun, and a Martian day, Sol, is slightly longer than an Earth day, lasting about 24 hours and 39 minutes. This section will cover how Mars's orbital and rotational dynamics contribute to its seasonal variations and overall climate. Human fascination with Mars dates back to ancient times. Early astronomers observed its reddish hue and movement across the sky. And in the 19th and early 20th centuries, there was speculation about the possibility of life on Mars, fueled by observations of what appeared to be canals and seasonal color changes. This historical overview will trace our understanding of Mars from these early observations through to the modern era of space exploration, highlighting key missions that have expanded our knowledge of the red planet. Mars has also been a staple of popular culture and science fiction, often depicted as a location for extraterrestrial life or human colonization. This part of the overview will touch on the cultural significance of Mars and how it has been portrayed in literature, film, and art, reflecting our species' long-standing fascination with this neighboring planet. The modern exploration of Mars began in the 1960s with flyby missions, followed by orbiters, landers, and rovers. Key missions such as NASA's Viking landers, Mars Pathfinder, the Mars exploration rovers, Spirit and Opportunity, the Mars Reconnaissance orbiter, and the Curiosity and Perseverance rovers have dramatically increased our understanding of the planet. This section will discuss the major milestones in Mars exploration, including the discoveries and technological advancements that have been made. One of the primary goals of Mars exploration has been the search for signs of past or present life. The overview will delve into the ongoing research and future missions aimed at understanding whether life ever existed on Mars. It will also discuss plans for human missions to Mars, including the challenges and potential timelines for these ambitious endeavors. The journey to uncover Mars' watery past begins with the earliest telescopic observations. In the 19th century, astronomers like Giovanni Schiaparelli and Percival Lowell observed features on Mars that were interpreted as canals, leading to speculation about the presence of liquid water and even a Martian civilization. Although these canal theories were later debunked, they sparked widespread interest and set the stage for future explorations. The Mariner missions of the 1960s and 1970s provided the first close-up views of Mars, revealing a world with craters, canyons, and intriguing surface features. Mariner 9, in particular, discovered evidence of riverbeds, valleys, and basins, suggesting that liquid water had once flowed on the Martian surface. NASA's Viking 1 and 2 missions in the mid-1970s were the first successful landers on Mars. They conducted experiments to search for life and also studied soil and atmospheric composition. While no definitive evidence of life was found, the Viking missions strengthened the hypothesis that Mars once had a more Earth-like climate, capable of supporting liquid water. In the late 1990s, the Mars Pathfinder lander and its Sojourner rover, along with the Mars Global Surveyor orbiter, brought back a wealth of data. They revealed ancient floodplains, sedimentary layers, and mineral deposits that form in the presence of water, adding more pieces to the puzzle of Mars' watery history. The twin rovers, Spirit and Opportunity, landing on Mars in 2004, made groundbreaking discoveries. Opportunity found evidence of hematite, a mineral often formed in water, and uncovered layers of rocks that indicated the past presence of flowing water. Spirit discovered silica deposits, which on Earth typically form in hot springs and other water-rich environments. In 2008, the Phoenix lander confirmed the presence of water ice in the Martian soil near its polar region. The lander's robotic arm scraped away layers of soil, revealing ice that sublimated, turned from solid to gas, when exposed to the Martian atmosphere. NASA's Curiosity rover, landing on Mars in 2012, made one of the most significant discoveries: ancient riverbeds and evidence of a lake that could have supported microbial life. Curiosity also detected organic molecules, the building blocks of life, further supporting the theory that Mars once had conditions favorable for life. The Mars Reconnaissance Orbiter has been instrumental in providing detailed images and data about Mars's surface. It has identified clay and sulfate minerals associated with water and mapped channels and deltas carved by ancient rivers. Analysis of Martian meteorites, along with data from various missions, has offered insights into Mars's climate history. These studies indicate that Mars had a significantly warmer and wetter climate in its early history, which could have supported liquid water on its surface. Recent discoveries about recurring slope lineae, dark streaks that appear seasonally on Martian slopes, and the detection of perchlorates, a type of salt that can lower the freezing point of water, have added complexity to our understanding of water on Mars. These findings suggest that briny liquid water might still occasionally flow on Mars's surface today. The historical evidence of water on Mars has significant implications for the planet's past habitability. The presence of water, along with the detection of organic compounds, suggests that Mars may have had the necessary conditions to support life, at least in its microbial form, in the distant past. This comprehensive review of the historical evidence of water on Mars combines data from multiple missions and scientific studies. By piecing together this evidence, scientists have been able to reconstruct a picture of a planet that was once very different from the cold, dry world we see today. Mars's surface is home to numerous geological formations that suggest the presence of liquid water in its ancient past. One of the most compelling pieces of evidence is the network of valleys and channels resembling those formed by water erosion on Earth. These features, such as the outflow channels of Chrysoplanitia and the ancient river valleys of Margaritifer Sinus, indicate that large volumes of water once flowed across the Martian surface. Sedimentary structures, especially those discovered by the rovers exploring Mars, provide crucial clues about the planet's watery past. The sedimentary rocks observed by the Curiosity rover in Gale Crater, for instance, contain fine layers and ripple marks typical of rock formations created in ancient lakes or rivers. These sedimentary deposits suggest that Gale Crater once held a lake or a series of lakes over an extended period. Minerals on Mars, particularly those detected by orbiters and rovers, also hint at the planet's watery history. The presence of clay minerals, sulfates, and silicates indicates chemical alteration by water. These minerals are often found in environments on Earth where water has been present for long periods. The discovery of hydrated minerals, which contain water molecules within their crystalline structure, further supports the idea of ancient, persistent water on Mars. Mars' polar ice caps, composed of layers of water ice and dust, provide insights into the planet's climatic history. These ice caps, especially the northern cap with its layers of water ice and frozen carbon dioxide, are akin to Earth's polar regions and suggest that Mars was once cold enough for water to freeze at the poles. Additionally, the widespread permafrost found just beneath the Martian surface implies that water was once more abundant and has since been locked away as ice. The study of Martian impact craters has revealed evidence of hydrothermal systems, which could have been created by the heat from impacts melting subsurface ice. These hydrothermal systems could have provided warm, water-rich environments that were potentially habitable. Craters like Gusev, explored by the Spirit rover, have shown signs of past water activity and hydrothermal deposits. Analysis of atmospheric isotopes, particularly by the MAVEN mission, has provided insights into Mars's ancient climate. The ratios of certain isotopes in the Martian atmosphere can be used to infer the history of water loss from the planet. These findings, combined with climate models, suggest that Mars was once warm enough to sustain liquid water on its surface, possibly due to a thicker atmosphere and a stronger greenhouse effect. The discovery of river deltas and ancient lake beds on Mars is among the strongest evidence for long-standing water bodies. These formations, similar to those found on Earth, indicate that water once flowed into basins, creating lakes or even seas. Jezero Crater, the landing site of the Perseverance rover, is particularly notable for its well-preserved river delta, suggesting that the crater was once a lake. The orbital and axial dynamics of Mars have played a significant role in its climatic history. Variations in Mars's orbit and tilt could have led to significant climate changes, including periods warm and wet enough to allow liquid water to exist. This part of the section will explore how shifts in Mars's orbit and axis might have impacted its climate and water availability. By comparing Earth's geological and hydrological history with that of Mars, scientists gain a better understanding of planetary evolution and the conditions necessary for sustaining liquid water. This comparison highlights the unique pathways each planet has taken, with Mars losing most of its water and atmosphere, leading to the cold, arid conditions we observe today. The Martian landscape, etched with numerous features indicative of water flow, provides compelling evidence of the planet's aqueous past. This section will explore the key geological formations on Mars that hint at the historical presence and movement of water. One of the most striking features suggestive of past water flow on Mars are the extensive networks of river valleys. These valleys, similar in appearance to those formed by rivers on Earth, are found in various regions of Mars and indicate that water once flowed across the surface. The outflow channels, massive and often originating in the southern highlands, are believed to have been formed by catastrophic flood events. These channels, such as Ares Valley, evidence of ancient lake beds comes from the detection of sedimentary layers that are typically formed in calm water environments. Gale Crater, explored by the Curiosity rover, contains stacked layers of sedimentary rock that suggest it was once the site of a long-standing lake. The fine layering within these rocks indicates a calm and persistent water environment suitable for the gradual deposition of sediments. The mineralogical evidence on Mars further attests to the planet's watery history. Minerals such as clays, sulfates, and carbonates are often formed in the presence of water and have been detected in various Martian locations. The presence of hydrated minerals, which contain water within their molecular structure, is particularly telling. These minerals, found in places like Mawrith Vallis and Syrtis Major, suggest that water not only flowed but also interacted with the Martian rocks, altering their chemical composition. Gullies observed on Martian slopes and crater walls are reminiscent of those formed by flowing water on Earth. Some of these features are thought to be relatively recent, suggesting that liquid water might still occasionally flow on the surface of Mars. The recurring slope lineae, dark streaks appearing seasonally on steep slopes, are hypothesized to be formed by the flow of briny water, although this remains a subject of active research and debate. The polar ice caps of Mars, particularly the northern cap, show evidence of glacial movement and meltwater formation. The layered deposits in these caps, consisting of dust and ice, reveal a history of climatic changes and suggest that water ice was once more prevalent across the Martian surface. Glacial-like features such as moraines and drumlins observed in other regions indicate that glaciers may have once been active on Mars, shaping the landscape through the movement of ice. Impact craters on Mars have provided valuable insights into the planet's hydrologic history. Some craters show evidence of lakes formed by the melting of ice due to the heat of the impact. Others, like Holden Crater, contain sedimentary deposits and layered terrains indicative of prolonged water presence and possibly a lake environment. Atmospheric and climate models of ancient Mars support the geological evidence of water flow. These models suggest that Mars once had a thicker atmosphere, capable of sustaining higher temperatures and a hydrological cycle that included rain and snow. This would have allowed for the formation of rivers, lakes, and perhaps even oceans, leaving the geological signatures we observe today. The discovery of sedimentary rocks and ancient lake beds on Mars has been a game-changer in our understanding of the red planet's past. These features serve as geological archives, capturing evidence of environmental conditions that prevailed billions of years ago, when water was more abundant on Mars. Sedimentary rocks on Mars are formed in much the same way as they are on Earth, through the accumulation and compaction of sediments. These sediments can be transported by water, wind, or ice, but the presence of certain types of sedimentary rocks, particularly those found in layers, strongly suggests aqueous origins. This section will delve into how the presence of sedimentary rocks on Mars indicates past water activity, including the transportation and deposition of sediments in a liquid environment. NASA's Curiosity rover has provided invaluable insights into Mars's past by studying the sedimentary rocks in Gale Crater. The crater, believed to have once been a lake, exhibits a stack of sedimentary layers, which Curiosity has analyzed in detail. These layers show fine gradations that are characteristic of sediments laid down in calm water. The varied composition of these layers further suggests changing environmental conditions, possibly reflecting cyclic changes in the Martian climate. Clay minerals detected in Martian sedimentary rocks are significant because they typically form in the presence of water. The discovery of clays in several locations on Mars, such as Marth Valles and the ancient lake beds within Gale Crater, points to a time when water was stable on the surface, providing conditions necessary for the formation of these minerals. In addition to clays, the presence of sulfate and carbonate minerals in Martian sedimentary rocks tells a story of evaporating lakes and changing environmental conditions. These minerals often form when water evaporates, leaving behind concentrated minerals. Their presence suggests that Mars experienced periods of wet and dry cycles, consistent with the existence of lake-like environments. The exploration of Jezero Crater, particularly by the Perseverance rover, has been instrumental in understanding Mars's lacustrine history. Jezero contains a well-preserved river delta, indicative of a long-standing lake that received sediment from a river. Analyzing the sediments in this delta will help reconstruct the climate history of Mars and determine the habitability of these ancient lake environments. The stratigraphy, or layering of Martian lake beds, provides vital clues about the environmental conditions over time. Variations in layer thickness, mineral composition, and sediment types can indicate changes in water depth, flow rates, and even climate conditions. By studying these layers, scientists can piece together a more detailed picture of Mars's climatic history. The evidence of sedimentary rocks and ancient lake beds on Mars has significant implications for the planet's potential to support life. On Earth, such environments are often rich in biodiversity. While it is not yet known if life ever existed on Mars, these aquatic environments would have been the most likely places for it to develop, providing a stable, water-rich habitat with the necessary chemical ingredients for life. Comparing sedimentary processes and lakebed formations on Mars with those on Earth helps scientists understand the similarities and differences in planetary geology and hydrology. This comparison provides insights into the conditions necessary for the formation and sustainability of liquid water bodies on terrestrial planets. Future Mars missions and research will continue to focus on sedimentary rocks and ancient lake beds to unravel the mysteries of Mars' past. Missions like the Mars Sample Return mission aim to bring back samples of these rocks for detailed analysis on Earth, potentially revealing new insights into the planet's history and its capacity for life. Mars is a planet of contrasts, and its polar regions are among the most striking and informative. The Martian polar ice caps, along with widespread permafrost, are key to understanding the planet's climatic history and water cycle. Mars hosts 2 polar ice caps, each with distinct compositions and seasonal behaviors. The northern cap, Planemborium, is primarily composed of water ice mixed with dust and is larger and less steep than its southern counterpart. The southern cap, Planum Australe, contains more dry ice, frozen carbon dioxide, and undergoes significant size changes with the Martian seasons. This section will detail the structure, composition, and seasonal variations of these polar ice caps. The polar ice caps of Mars, much like Earth's, contain layers that serve as records of the planet's past climate. These layers, visible in radar observations, represent different periods of accumulation and can reveal information about past atmospheric conditions, dust storms, and climatic changes. Analyzing the stratigraphy of these ice layers helps scientists reconstruct Mars's climatic history. Permafrost on Mars is an extensive feature, covering a significant portion of the planet's surface. Martian permafrost is similar to Earth's, consisting of soil or rock that has remained frozen for long periods. This frozen ground holds a large reservoir of water ice, offering clues about the planet's water cycle and past conditions that allowed for the accumulation and preservation of ice. Recent discoveries have indicated the presence of subsurface ice sheets at mid-latitudes, far from the polar regions. These ice deposits are believed to be remnants of ancient glaciers or ice sheets and could be extensive, lying just beneath the surface. Understanding these subsurface ice reserves is crucial for piecing together Mars's hydrological history. The polar ice caps and permafrost are key elements in Mars's water cycle. They represent current water reserves and provide insights into the planet's ability to support ice, and by extension, liquid water in the past. This section will explore the implications of these ice reserves for Mars' past habitability, including the potential for the ice to have supported microbial life. Beyond their climatic significance, the polar regions of Mars play a crucial role in the planet's geology. Features such as polar layered deposits, spiral troughs, and chasms provide unique insights into the geologic processes at work on Mars. These features are shaped by a combination of ice dynamics, sublimation processes, and Martian weather patterns. A variety of tools and techniques are used to study the Martian polar regions and permafrost, including orbiters equipped with radar, imaging systems, and spectrometers. Landers and rovers have also contributed to our understanding, though they have yet to explore the polar regions directly. Future missions may target these areas specifically to gain more detailed insights. The presence of ice on Mars has significant implications for future human exploration and potential colonization. Ice can be a vital resource, providing water for human consumption, agriculture, and oxygen production. The accessibility of ice, particularly near the surface, will be a key factor in selecting sites for future manned missions. Mars, once brimming with liquid water, underwent a dramatic transformation in its history. Today's dry, dusty surface stands in stark contrast to the evidence of ancient rivers, lakes, and possibly even oceans. Understanding how Mars lost its water is crucial for piecing together the planet's history and its prospects for life. One of the primary theories in explaining Mars's water loss involves the thinning of its atmosphere. Unlike Earth, Mars lacks a strong magnetic field to protect its atmosphere from the solar wind streams of charged particles emitted by the Sun. Over billions of years, these particles are thought to have stripped away much of Mars's atmosphere, a process observed by missions like NASA's MAVEN, Mars Atmosphere and Volatile Evolution spacecraft. This atmospheric erosion reduced the greenhouse effect necessary to keep the planet warm and support liquid water on its surface. The role of the solar wind in eroding Mars's atmosphere is closely tied to the loss of its magnetic field. Mars likely had a magnetic field early in its history, generated by a dynamo effect in its molten core. As the planet cooled and its dynamo ceased, Mars lost this magnetic shield, exposing its atmosphere to solar wind stripping. Theories suggest that this process accelerated the loss of water by allowing hydrogen, a component of water, to escape into space. Another theory posits that significant climate change contributed to Mars's water loss. As Mars's atmosphere thinned, it could no longer retain sufficient heat, leading to planetary cooling. This cooling could have caused surface water to freeze, trapping it in the polar ice caps and underground as permafrost, effectively removing it from the active hydrological cycle. The decline in Mars's geological activity may also have played a role in its water loss. On Earth, tectonic activity helps recycle water between the surface and interior. Mars' lack of active plate tectonics could mean that water became trapped underground and was not recycled back to the surface. Additionally, volcanic activity, which can release water vapor and other gases into the atmosphere, diminished over time on Mars, further reducing the replenishment of water and other volatiles in the atmosphere. The impact of meteorites and asteroids has also been considered as a mechanism for water loss. Large impacts could have generated enough heat to vaporize surface water and blast it into space. However, this theory is less favored as a major contributor to water loss, as it would require an impractically high frequency of large impacts. Most scientists agree that no single factor is solely responsible for Mars's water loss. Instead, it is likely a combination of several processes, including atmospheric erosion by the solar wind, the loss of magnetic field, reduced volcanic activity, and planetary cooling. Each of these factors contributed to the gradual disappearance of liquid water from the surface, leaving Mars in its current state. Supporting evidence for these theories comes from the analysis of isotope ratios in the Martian atmosphere. The ratios of certain isotopes of hydrogen and other elements provide clues to the history of water loss. For example, a higher proportion of the heavier isotope deuterium compared to hydrogen suggests that lighter hydrogen escaped into space over time. Understanding water loss on Mars also involves comparing it with Earth. This comparative planetology approach helps scientists understand why two planets, starting with similar conditions, could have such divergent paths. Mars's smaller size, weaker gravity, and lack of a sustained magnetic field are all factors that contributed to its different evolutionary path. The theories about water loss on Mars have significant implications for the search for life. If Mars once had stable, long-lasting water bodies, it might have supported microbial life. Understanding how and when Mars lost its water can help pinpoint when life might have existed and guide future missions in their search for life signs. Mars' current thin and cold atmosphere stands in stark contrast to the evidence suggesting a much thicker and warmer atmosphere in the past, capable of supporting liquid water. The process of atmospheric escape is key to understanding how Mars underwent this dramatic transformation. Atmospheric escape refers to the process in which a planet loses its atmospheric gases to space. For Mars, this has primarily occurred through non-thermal processes like solar wind stripping and sputtering, along with thermal escape mechanisms. This section will explain these processes in detail, highlighting how they have contributed to the gradual thinning of Mars's atmosphere over billions of years. One of the primary factors in Mars's atmospheric escape is the solar wind, a stream of charged particles emitted by the sun. Early in its history, Mars likely had a magnetic field similar to Earth's, which protected its atmosphere from the solar wind. However, as the planet's dynamo ceased, possibly due to cooling of its core, Mars lost this protective shield. Without a magnetic field, the solar wind began to directly interact with the Martian atmosphere, stripping away particles and leading to significant atmospheric loss. Sputtering is a process where energetic particles in the solar wind collide with atmospheric gases, knocking them into space. This mechanism has been particularly effective in removing lighter gases, such as hydrogen, which is a key component of water. Understanding the rate and impact of sputtering is crucial in quantifying how much of Mars's atmosphere has been lost through this process. Thermal escape is another mechanism contributing to atmospheric loss. In this process, atoms or molecules in the upper atmosphere gain enough kinetic energy, often through heat, to overcome the planet's gravitational pull and escape into space. Mars' smaller size and weaker gravity compared to Earth make it more susceptible to thermal escape, particularly for lighter gases like hydrogen. The evidence for atmospheric escape on Mars comes primarily from the analysis of isotope ratios. Heavier isotopes of certain elements, like deuterium, a heavier form of hydrogen, are left behind as lighter ones escape. Mars has a much higher deuterium to hydrogen ratio than Earth, strongly indicating significant hydrogen loss from the atmosphere over time. NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission, has been pivotal in studying Mars's atmospheric escape. MAVEN's observations and measurements have provided detailed insights into how the solar wind and ultraviolet radiation from the sun have driven atmospheric escape processes. This section will delve into the key findings from MAVEN and their implications for understanding Mars's climatic evolution. By comparing Mars's atmospheric escape with that of Earth and Venus, scientists can gain insights into the different factors that influence a planet's ability to retain its atmosphere. Earth's strong magnetic field and Venus's thick atmosphere offer contrasting cases to Mars, helping to shed light on the various paths planetary atmospheres can take under different conditions. The loss of Mars's atmosphere due to atmospheric escape has had profound implications for the planet's climate and habitability. As the atmosphere thinned, Mars lost its ability to retain heat, leading to a colder environment where liquid water could no longer exist on the surface. This section will explore the implications of atmospheric escape for the potential for life on Mars, both past and present. Understanding atmospheric escape on Mars is not just about reconstructing the planet's past. It also has implications for future exploration and the search for life. Future missions may focus on measuring current rates of atmospheric loss and exploring how these processes have shaped the Martian surface and subsurface environments. Mars presents a unique case in planetary science due to its low gravity and lack of a global magnetic field. These factors have played crucial roles in the planet's atmospheric evolution, particularly in the loss of its atmosphere and water reserves. Gravity is a fundamental force that holds a planet's atmosphere in place. Mars, being only about 10% the mass of Earth, has a significantly weaker gravitational pull. This lower gravity has a direct impact on the planet's ability to retain its atmosphere, especially lighter gases such as hydrogen and helium, which are essential components of water and other vital compounds. In planetary atmospheres, lighter gases move faster than heavier gases at a given temperature. Due to Mars's lower gravity, these gases can reach escape velocity more easily compared to a planet like Earth. This means that over time, Mars has been more susceptible to losing its atmosphere to space, a process exacerbated by other factors such as solar wind and thermal escape. A magnetic field serves as a protective shield against solar wind, a stream of charged particles emitted by the sun. Early in its history, Mars likely had a magnetic field, generated by a dynamo effect in its molten core. However, as the planet's interior cooled and its volcanic activity decreased, this dynamo effect weakened and eventually ceased. Without a magnetic field to deflect the solar wind, Mars's atmosphere became directly exposed to these charged particles. This exposure has allowed the solar wind to gradually strip away the Martian atmosphere, particularly during periods of intense solar activity. The solar wind can directly strip atmospheric particles and also induce processes like sputtering, where incoming solar particles knock atmospheric molecules into space. Despite the absence of a current global magnetic field, Mars shows evidence of past magnetism in the form of crustal magnetic anomalies. These regions, detected by orbiting spacecraft, suggest that parts of Mars' crust were magnetized when the planet still had a magnetic field. The distribution and strength of these anomalies provide clues about the history and decay of Mars' magnetic field. A comparison with Earth highlights the protective role of a magnetic field. Earth's magnetic field deflects the solar wind, limiting the loss of atmosphere and maintaining a stable environment for liquid water. Mars's experience demonstrates the consequences of losing this protective shield, particularly for planetary habitability. The combination of low gravity and lack of a magnetic field has direct implications for Mars's ability to retain water. As the atmosphere thinned, the pressure on the Martian surface decreased, lowering the boiling point of water. This change likely contributed to the rapid evaporation and loss of any surface water, shifting Mars from a potentially habitable world to the arid and cold planet we see today. The interplay of low gravity and the absence of a magnetic field is key to understanding how Mars transitioned from a wetter, warmer past to its current state. These factors, coupled with geological changes and solar radiation, have shaped the Martian climate over billions of years, resulting in the loss of most of its surface water and a significant portion of its atmosphere. Future Mars missions and research will continue to focus on these aspects to gain a deeper understanding of Mars' atmospheric and hydrological history. This includes studying the planet's gravity field in more detail, examining the remnants of its magnetic field, and understanding the current rate of atmospheric escape. Mars, once home to vast amounts of water, has undergone a significant loss of hydrogen and oxygen, the fundamental elements of water. This section investigates the mechanisms behind their escape and the consequential effects on the Martian environment. Hydrogen, being the lightest element, escapes Mars's atmosphere more easily than heavier gases. This escape primarily occurs through thermal processes, where hydrogen molecules gain enough kinetic energy to exceed Mars's escape velocity. The lack of a protective magnetic field and the planet's relatively low gravity further facilitate this escape. A significant process contributing to hydrogen escape is the photochemical dissociation of water. Ultraviolet radiation from the sun breaks down water vapor in the upper atmosphere into hydrogen and oxygen. While heavier oxygen atoms are more likely to remain gravitationally bound to Mars, the lighter hydrogen atoms can escape into space. The evidence for hydrogen escape is found in the deuterium to hydrogen DH ratio in the Martian atmosphere. Deuterium, a heavier isotope of hydrogen, is less likely to escape. Over time, as lighter hydrogen escapes, the DH ratio increases. Mars has a significantly higher DH ratio compared to Earth, indicating substantial hydrogen loss over its history. Oxygen escape on Mars, though less significant than hydrogen, still plays a critical role in the planet's atmospheric and hydrological changes. The escape mechanisms for oxygen include thermal processes and chemical reactions in the upper atmosphere, where oxygen atoms can be energized or ionized to speeds that allow them to escape Mars' gravitational pull. The solar wind, particularly during periods of high solar activity, can contribute to oxygen loss. Energetic particles from the solar wind can collide with Martian atmospheric gases, leading to the acceleration of oxygen atoms to escape velocities. Coronal mass ejections, CMEs, from the Sun, which are massive bursts of solar wind and magnetic fields, can significantly enhance the escape of atmospheric gases, including oxygen. During these events, the increased solar wind pressure and energy can strip away parts of the upper atmosphere, leading to a spike in atmospheric escape rates. The escape of hydrogen and oxygen has direct implications for Mars's water reserves. Since water is composed of these two elements, their loss translates into a gradual depletion of water. This process has been a significant factor in Mars transitioning from a wetter, potentially habitable world to the arid planet we see today. The loss of water vapor, a greenhouse gas, also affects Mars's climate. As the planet loses water, it also loses some of its ability to retain heat, leading to further cooling. This cooling can lead to more water freezing out of the atmosphere, creating a feedback mechanism that exacerbates the loss of liquid water. NASA's MAVEN mission has provided key insights into the current rates of atmospheric escape on Mars, including the loss of hydrogen and oxygen. MAVEN's measurements help scientists estimate the total amount of water lost over time and understand the processes driving this loss. The gradual loss of water has profound implications for Mars's geology and potential habitability. The transformation from a wet to a dry environment has altered the planet's surface and atmosphere, impacting the potential for life. Understanding this transformation helps in piecing together the puzzle of Mars's past and assessing its potential for supporting life in its early history. Future missions and research will continue to focus on quantifying the loss of hydrogen and oxygen from Mars. This research is not only critical for understanding Mars's past, but also for planning future missions, particularly those aimed at human exploration and potential in-situ resource utilization. Mars, currently a cold and dry planet, shows evidence of a past marked by warmer and wetter conditions. This section delves into the factors behind this dramatic climatic evolution, shedding light on the complex interplay of processes that have shaped the Martian environment. One of the key drivers of climate change on Mars has been the loss of its atmosphere. As Mars's atmosphere thinned, primarily due to solar wind stripping and the absence of a magnetic field, its ability to trap heat diminished. This loss of a substantial atmosphere led to a decrease in surface temperatures and a shift in the planet's ability to support liquid water. The thinning of Mars's atmosphere reduced the greenhouse effect, a natural process where certain gases trap heat in a planet's atmosphere. On Mars, this reduction in the greenhouse effect led to a decline in surface temperatures, making it increasingly difficult for liquid water to exist. Mars's geological activity, including volcanic eruptions, has played a significant role in its climate. Volcanic activity can release gases into the atmosphere, contributing to the greenhouse effect. However, as Mars's geological activity diminished over time, so did its replenishment of greenhouse gases, contributing to a cooling climate. Changes in solar radiation over time have also influenced Mars's climate. The sun has gradually become brighter over billions of years. However, this increased solar output has not been sufficient to counteract the cooling effects of Mars's atmospheric loss and reduced volcanic activity. Mars experiences variations in its orbit and axial tilt, known as Milankovitch cycles, which can significantly impact its climate. These cycles affect the distribution of sunlight on the planet's surface, leading to changes in temperature and ice distribution. They may have contributed to periods of warmer and wetter conditions, as well as colder, drier episodes. Meteorite and asteroid collisions have episodically altered Mars's climate. Large impacts can throw dust and debris into the atmosphere, temporarily changing the planet's albedo, reflectivity, and atmospheric composition. These events can lead to short-term climatic changes, including temperature fluctuations. The geological features of Mars, such as dry riverbeds, lake deposits, and sedimentary layers, offer evidence of its climatic past. Additionally, the polar ice caps, composed of layers of ice and dust, act as climatic archives, recording changes in Mars's atmosphere and temperature over time. NASA's MAVEN mission has provided valuable insights into Mars's current atmospheric composition and its evolution, shedding light on how changes in the atmosphere have influenced the planet's climate. These findings help piece together the timeline of Mars' climatic changes. The climatic changes on Mars have direct implications for the planet's water availability and its potential to support life. As Mars transitioned to a colder, drier state, any existing liquid water became locked in the polar ice caps or underground as permafrost, impacting the potential habitability of the planet. Scientific models play a crucial role in understanding Mars's climate evolution. These models integrate data from geological observations, atmospheric composition, and solar radiation to reconstruct the planet's climatic history and predict future changes. Comparing Mars's climatic evolution with Earth's provides valuable perspectives on planetary climates and the factors that influence them. This comparative planetology helps identify the unique conditions that have allowed Earth to sustain a stable, life-supporting climate, in contrast to Mars. Continued research and exploration are essential for deepening our understanding of Mars's climate change. Future missions and studies will focus on refining our knowledge of Mars's past climate, including the role of water in shaping its surface and the potential for past life. Mars's evolution from a planet that once likely had liquid water with a potentially warm and wet climate to the desolate, frozen desert we see today is a story of planetary transformation. This section explores the factors behind this dramatic shift in climate and environment. Geological evidence, including the presence of ancient river valleys, lake beds, and mineral deposits, suggests that Mars once had a significantly warmer and wetter climate. This would have allowed liquid water to exist on the surface, shaping the Martian landscape through erosion and sedimentation. In its early years, Mars is believed to have had a thicker atmosphere, rich in carbon dioxide and possibly other greenhouse gases. This thicker atmosphere would have created a stronger greenhouse effect, trapping heat and warming the planet's surface, making it conducive to liquid water. Over time, Mars lost much of its atmosphere to space, primarily due to solar wind stripping away the lighter molecules, a process exacerbated by the planet's weak gravity and lack of a global magnetic field. This loss of atmosphere led to a significant decline in the greenhouse effect, causing the planet to cool. As Mars cooled, any surface water began to freeze or evaporate into the thinning atmosphere, where it was then lost to space. The cooling also led to the ground becoming permanently frozen, creating the extensive permafrost observed today. Mars's volcanic activity played a crucial role in its early climate. Volcanoes can release gases like water vapor and carbon dioxide, both potent greenhouse gases. However, as the planet's volcanic activity waned, so did the replenishment of these greenhouse gases, contributing to the cooling climate. Mars's orbit and axial tilt have varied over time, affecting its climate. These variations, known as Milankovitch cycles, can lead to significant climatic changes, including global temperature fluctuations and shifts in the distribution of ice and water. The sun has evolved over billions of years, becoming brighter and hotter. However, this increased solar output was not enough to counteract the effects of Mars's atmospheric loss and cooling. The breakdown of the Martian hydrological cycle was a key aspect of its climatic transition. As the planet cooled and the atmosphere thinned, the cycle of evaporation and precipitation of water that drives a dynamic climate was disrupted, leading to the arid conditions we see today. The Martian polar ice caps, containing layers of ice and dust, provide a historical record of the planet's climatic changes. These ice caps suggest periods of ice accumulation and retreat, reflective of past climatic fluctuations. The geological record of Mars tells a story of transition from an active, water-rich environment to a static, arid landscape. The once flowing rivers gave way to dry riverbeds, and the lake beds turned into barren plains, indicating a shift from a wet to a dry climate. This climatic transition raises questions about the potential for life on Mars. In its early, warmer, and wetter era, Mars might have had conditions suitable for life, especially microbial life. As the climate changed, any potential life would have had to adapt to increasingly harsh conditions. The MAVEN mission has been instrumental in understanding Mars's atmospheric loss, providing insights into how this process has driven climatic changes. The data from MAVEN helps reconstruct the timeline of Mars's atmospheric and climatic evolution. Future missions to Mars, including rover explorations and sample return missions, aim to gather more data on the planet's climatic history. These missions are critical for understanding the processes that led to the current Martian environment and for assessing the planet's past habitability. Mars, like Earth, experiences changes in its climate due to variations in its axial tilt and orbit. These changes, often subtle yet significant over long periods, have played a crucial role in shaping the Martian environment. Mars' axial tilt has varied considerably over millions of years, ranging from about 15 degrees to 35 degrees compared to its current tilt of approximately 25 degrees. This tilt, or obliquity, significantly influences the planet's seasons and climate. A higher tilt leads to more extreme seasons, while a lower tilt results in milder seasonal changes. In addition to axial tilt, Mars's orbit around the Sun is not a perfect circle, but an ellipse, eccentricity, and this elliptical orbit also precesses or wobbles over time. These factors contribute to variations in the amount of solar energy Mars receives, further impacting its climatic conditions. Changes in axial tilt and orbital variations alter the intensity and duration of Martian seasons. When the tilt is higher, the poles receive more direct sunlight, potentially leading to significant melting of the polar ice caps and increased atmospheric water vapor, which could affect global weather patterns. Mars' polar ice caps are sensitive indicators of climatic change. Fluctuations in axial tilt can lead to substantial redistribution of ice from polar regions to mid-latitudes. This redistribution can result in the growth or shrinkage of ice caps, as well as changes in the planet's albedo, reflectivity, which further influence climate. The axial tilt and orbital variations of Mars are believed to have caused historical shifts in its climate. These shifts could explain the evidence of past water flow, such as dried-up riverbeds and lake basins, suggesting periods of warmer and wetter conditions. Scientists use computer models to simulate how changes in axial tilt and orbital patterns might have affected Mars's climate over millions of years. These models help in understanding past climatic conditions and predicting future changes, offering insights into the dynamics of Martian weather and environmental conditions. Similar to Earth's Milankovitch cycles, which involve changes in Earth's orbit and tilt affecting its ice ages and warm periods, Mars experiences its own cycles. However, due to Mars's more pronounced axial tilt variations and a more eccentric orbit, these cycles can have more extreme effects on its climate. The changes in climate driven by axial tilt and orbital variations have implications for the potential habitability of Mars. Periods of warmer and wetter conditions might have made Mars more hospitable to life, at least temporarily, increasing the likelihood of microbial life during these periods. Geological studies, including analysis of sedimentary layers and ice core samples from polar caps, provide evidence of past climatic changes on Mars. These studies help trace the history of water and ice on the planet, correlating it with astronomical cycles. Future Mars missions and research will aim to gather more data on the planet's axial tilt and orbital history. This research is crucial for a comprehensive understanding of Mars's climate evolution and its response to astronomical influences. Despite its arid and inhospitable surface, Mars still holds water in various forms. Understanding the current state of water on Mars is crucial for studying the planet's history and planning future exploration. The most substantial known reserves of water on Mars are at its polar ice caps. The North Pole's Planum boreum and the South Pole's Planum austral consist primarily of water ice mixed with frozen carbon dioxide, dry ice. These ice caps contain layered deposits, preserving a record of Mars' climatic history. Beyond the polar caps, significant amounts of water ice are buried beneath Mars's surface, particularly in its northern plains. Radar data from missions like Mars Reconnaissance Orbiter, MRO, have revealed extensive subsurface ice deposits at mid-latitudes. These deposits are believed to be remnants of ancient glaciers and could be a key resource for future manned missions. In addition to permanent ice deposits, Mars experiences seasonal frost and ice. During winter, temperatures drop low enough for water vapor in the atmosphere to condense and freeze, forming thin layers of frost, particularly in the polar regions. Mars's atmosphere contains small amounts of water vapor, the amount of which varies seasonally and regionally. The water cycle on Mars, involving sublimation, condensation, and deposition of water ice, is much more limited compared to Earth, but it still plays a role in the planet's climate and weather. The existence of liquid water on present-day Mars is a subject of ongoing research and debate. There have been observations such as recurring slope lineae, RSL, which suggest the potential presence of transient liquid water. These dark streaks appear to flow downhill in warmer seasons, possibly due to briny, salty water, but they remain a topic of active study. The presence of salts or perchlorates in the Martian soil could lower the freezing point of water, allowing for the formation of transient briny liquid water under certain conditions. However, the extremely low temperatures and pressures on the Martian surface make the persistence of stable liquid water challenging. Much of Mars's surface is covered by permafrost, soil that remains frozen year-round. Drilling missions, such as the InSight lander's HP-3 instrument, aim to study these subsurface layers to understand the distribution and state of water ice below the surface. The current state of water on Mars has significant implications for the planet's habitability and the search for past or present life. Subsurface ice deposits could provide habitats for microbial life, and the history of water on Mars can offer clues about the planet's potential to have supported life in the past. Water on Mars is not only a scientific interest but also a practical resource for future human exploration. Ice deposits could be mined for drinking water, oxygen, and even fuel. Understanding the distribution and accessibility of water on Mars is a key factor in planning future manned missions. The quest to understand the current state of water on Mars continues with ongoing and future missions. Rovers like Perseverance and upcoming missions, including ice mapping and sample return missions, aim to shed further light on the distribution, history, and state of Martian water. Mars, with its cold and thin atmosphere, hosts various forms of ice and frost, ranging from permanent ice caps to seasonal frost deposits. These features provide critical insights into the Martian climate and water cycle. The most prominent sources of residual ice on Mars are its polar ice caps. These caps consist mainly of water ice with a seasonal covering of dry ice, frozen carbon dioxide. The northern cap, Planum boreum, and the southern cap, Planum austral, vary in size and composition with the Martian seasons, but retain a permanent base layer of water ice. Beyond the polar regions, Mars harbors extensive subsurface ice deposits, particularly in its northern hemisphere. These ice deposits, believed to be remnants of ancient glaciers, can extend several meters below the surface, offering significant reservoirs of water ice. In addition to permanent ice, Mars experiences seasonal frost. This frost forms when atmospheric water vapor condenses and freezes on the surface, usually during the colder Martian nights. Frost is most commonly observed in the polar regions, but can occur in mid-latitude areas during winter months. Martian frost differs from Earth's in several ways, primarily due to the thin Martian atmosphere and lower temperatures. The frost on Mars tends to be finer and less dense, and it sublimates, changes from solid to gas, quickly as temperatures rise. Frost on Mars has been observed and studied using a variety of methods, including satellite imaging, spectroscopy, and lander-based instruments. These observations help scientists understand seasonal and diurnal variations in Martian surface conditions. While limited compared to Earth, frost plays a role in the Martian water cycle. The seasonal deposition and sublimation of frost contribute to the redistribution of water vapor in the atmosphere, influencing local weather and potentially impacting soil chemistry. The presence and distribution of residual ice and frost on Mars offer clues to the planet's climatic history. By studying these ice deposits, scientists can infer past environmental conditions, including temperature fluctuations and atmospheric changes. For future manned missions to Mars, understanding the distribution and accessibility of ice and frost is crucial. These water sources could be utilized for drinking, oxygen production, and fuel, making them vital for sustained human presence on Mars. Current and future Mars missions continue to focus on studying ice and frost. Rovers like the Mars Science Laboratory, Curiosity, and Mars 2020, Perseverance, as well as orbiters like the Mars Reconnaissance Orbiter, play key roles in mapping and analyzing these water sources. Studying ice and frost on Mars comes with challenges. The planet's harsh environment, varying temperatures, and dust storms can affect the stability and visibility of frost, making continuous observation and analysis difficult. While the surface of Mars is predominantly dry and barren, its subsurface tells a different story. Beneath the Martian surface lies a world of water in various forms, including ice and hydrated minerals, which are key to understanding the planet's past and future. One of the most significant discoveries in recent Martian exploration is the widespread presence of subsurface ice. Radar data, particularly from the Mars Reconnaissance Orbiter, has revealed large areas of water ice buried just beneath the surface, especially in the planet's mid to high latitudes. This subsurface ice is thought to be remnants of ancient glaciers and is a critical component of Mars' current water inventory. The subsurface ice on Mars is believed to have formed under different climatic conditions, possibly when the planet's axis tilt was different, allowing for more significant snowfall and ice accumulation. Over time, these ice deposits became buried by dust and regolith, protecting them from sublimation. Another vital discovery has been the presence of hydrated minerals on Mars. These minerals, which include clays and sulfates, are formed in the presence of water and provide evidence that liquid water once interacted with the Martian surface and subsurface. The identification of these minerals, through orbital spectrometry and rover analyses, has been instrumental in reconstructing Mars's aqueous history. The study of hydrated minerals on Mars helps scientists understand the planet's geologic and climatic evolution. These minerals can indicate the past presence of water bodies, the pH and salinity of ancient waters, and the potential for habitable conditions in Mars history. Mars's subsurface hydration varies by region, with some areas showing significant concentrations of water ice or hydrated minerals. This variability is influenced by factors such as latitude, local topography, and geological history. Mars rovers and landers, including Curiosity and Perseverance, have played a crucial role in detecting and analyzing hydrated minerals. These missions have also provided insights into the depth, concentration, and composition of subsurface hydration. The presence of subsurface water and hydrated minerals is significant for considerations of past habitability and the potential for life on Mars. These resources provide the necessary conditions for life as we know it and are key targets in the search for past microbial life. For future human missions to Mars, the presence of subsurface water is of immense practical importance. Subsurface ice could be mined for drinking water and split into hydrogen and oxygen for fuel and breathable air, making human colonization and long-term exploration feasible. Accessing subsurface water on Mars presents significant technical challenges. Drilling operations need to contend with the Martian soil's properties, extreme temperatures, and the planet's lower gravity and thin atmosphere. Future missions to Mars, including the proposed Mars Ice Mapper mission, aim to further map and characterize subsurface water and hydrated minerals. These efforts are crucial for advancing our understanding of Mars' water history and preparing for human exploration. Mars rovers have become our primary tools in exploring and understanding the Red Planet. Each rover mission, equipped with advanced scientific instruments, has contributed significantly to our knowledge of Mars, uncovering its secrets piece by piece. Curiosity rover, a journey through Gale Crater. Since its landing in 2012, NASA's Curiosity rover has been exploring Gale Crater, revealing crucial information about the planet's geology and past habitability. Among its key discoveries, ancient riverbeds and lake environments, Curiosity has found evidence that Gale Crater once hosted liquid water, with signs of ancient riverbeds and a lake that could have supported microbial life billions of years ago. Complex organic molecules. The detection of complex organic molecules in Martian soil and rock samples suggests that the necessary building blocks for life were present. Variable methane levels. Curiosity's measurements of methane levels, which fluctuate seasonally, have raised questions about potential geological or even biological sources. Perseverance rover. The search for past life in Jezero Crater. The Perseverance rover, which landed in Jezero Crater in 2021, has a primary mission of seeking signs of ancient life and collecting samples for future return to Earth. Its significant findings include ancient delta and lake deposits. Perseverance has been studying the remnants of an ancient river delta, looking for sedimentary deposits that could hold signs of past microbial life. Sample collection for Mars. Sample return. The rover has been collecting rock and soil samples, which are planned to be returned to Earth in the future for detailed analysis. MOXIE experiment. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, has successfully produced oxygen from the Martian atmosphere, a significant step toward future human exploration. InSight. Lander. Delving into Mars' interior Marsquakes. InSight has detected hundreds of seismic events, or Marsquakes, shedding light on the planet's internal activity. Internal structure. The data from these Marsquakes is helping scientists understand the structure of Mars's crust, mantle, and core. These rovers have also been test beds for technological innovations. For instance, Perseverance's Ingenuity helicopter has demonstrated powered flight in Mars's thin atmosphere, opening new avenues for exploration. However, the rovers also face challenges, such as harsh environmental conditions and limited energy resources, which they must overcome to continue their missions. Both Curiosity and Perseverance are equipped with weather stations, providing continuous environmental monitoring. This data offers insights into current Martian weather and climate patterns, essential for understanding the planet's present-day environment. A central aspect of these missions is astrobiology. By analyzing rocks, soil, and atmospheric samples, the rovers seek clues about the possibility of past life on Mars. While definitive evidence of life has yet to be found, the discoveries made so far have significantly advanced our understanding of the planet's habitability. The findings from Mars rovers are shaping future exploration strategies. The evidence of past water and potential habitability is guiding the selection of sites for future missions, including manned missions. The rover's data are also crucial in planning how to utilize Martian resources, such as water and minerals, for sustained human presence. Water is essential for human exploration of Mars, not just for sustaining life, but also as a key resource for fuel and other materials. The presence and accessibility of water on Mars are therefore critical considerations in planning future manned missions. Drinking water. Vital for human survival, water can be extracted from Martian ice and purified for consumption. Oxygen. Production. Electrolysis of water can generate oxygen for breathing, reducing the need to transport large amounts of oxygen from Earth. Fuel production. Water can be split into hydrogen and oxygen, providing fuel for rockets and surface vehicles. This process could significantly reduce the cost and logistics of transporting fuel to Mars. Identifying and accessing Martian water reserves. The success of human missions to Mars depends on the ability to locate and access water resources. Subsurface ice deposits, particularly in the northern plains and at mid-latitudes, are promising targets. Rovers and orbiters are currently mapping these resources to identify potential landing sites where water is accessible. Drilling technology. Drilling into the Martian surface to access subsurface ice requires robust technology that can operate in Mars's harsh conditions. Melting and purification. Once accessed, ice must be melted and purified, necessitating reliable and efficient systems capable of handling this process in a low-temperature, low-pressure environment. Use of in situ resources, ISRU in situ resource utilization, ISRU, is a strategy for using Martian resources to support human missions. This approach includes extracting water from the Martian environment and using it to produce oxygen, fuel, and other materials, thereby reducing the dependence on supplies from Earth. The ability to utilize Martian water resources is not just important for initial exploration missions, but is also crucial for the long-term habitability and potential colonization of Mars. Sustainable access to water would enable more extended stays on the Martian surface and pave the way for permanent settlements. As we plan to use Martian water resources, environmental and ethical considerations must be taken into account. This includes ensuring that the exploitation of these resources does not contaminate the Martian environment, particularly if there is a chance of existing Martian life. Lessons from water management on Earth can be applied to Mars, especially in terms of sustainable and efficient use of water resources. Techniques such as recycling and conservation will be essential in the closed environments of Martian habitats. Future missions to Mars, both robotic and human, will need to focus on detailed surveys of water resources and the development of technologies for water extraction and utilization. Research in these areas is crucial for the feasibility and success of human exploration of Mars. The exploration and utilization of Martian water resources will likely be a collaborative international effort involving space agencies, private companies, and scientific communities from around the world. Such collaboration will be key in pooling resources, expertise, and technology to make human exploration of Mars a reality. In the context of human missions to Mars, water is more than a basic necessity for life. It is a critical resource for various operational and survival needs. Understanding and harnessing Mars's water resources is key to the success of long-duration space missions. The most immediate use of water on Mars is for sustaining human life. Water is essential for drinking, cooking, and hygiene. Given the impracticality and high cost of transporting large quantities of water from Earth, sourcing water directly from Mars is crucial. Water on Mars can be electrolyzed to produce oxygen, a vital component for breathing. This process involves splitting water molecules into oxygen and hydrogen, providing a renewable and efficient method to generate a breathable atmosphere in Martian habitats. For long-term missions or colonization, growing food on Mars will be essential. Water is a key resource for agriculture, enabling the growth of plants both for food and as part of life support systems to recycle carbon dioxide and replenish oxygen. Water can be used to produce hydrogen, a potential fuel for both surface vehicles and rockets. The ability to refuel vehicles on Mars will significantly increase the range and flexibility of surface exploration and potentially enable return missions back to Earth. Water has excellent properties for radiation shielding. Storing water in and around living quarters can help protect astronauts from Mars' harsh radiation environment, as the planet lacks a protective magnetic field and thick atmosphere like Earth's. Extracting water on Mars presents several challenges, including accessing subsurface ice, melting and purifying it for use, and doing so in an energy-efficient manner. Technologies for drilling, mining, and processing Martian water must be developed and tested for operation in the planet's extreme conditions. In situ resource utilization, ISRU, involves using Martian materials to support human missions. Developing ISRU technologies for water extraction and processing is crucial for reducing dependency on Earth-based supplies, making missions more sustainable and cost-effective. While most of Mars's water is in the form of ice, the search for liquid water is ongoing. Liquid water would be easier to extract and utilize than ice, and could provide insights into potential Martian life. Utilizing Martian water resources raises ethical and environmental questions. It is essential to ensure that exploration activities do not contaminate potential biospheres or irreversibly deplete critical resources. Technological advancements are essential for efficient water utilization on Mars. Research in water recycling, extraction methods, and energy-efficient processing techniques will play a critical role in preparing for human missions. The exploration and utilization of water on Mars is likely to be a global effort. Collaboration between countries and organizations will be necessary to pool resources, share knowledge, and develop the best strategies for water management on Mars. Experiences from the International Space Station, ISS, and analog missions on Earth are invaluable in preparing for Mars. These missions provide insights into water recycling, closed-loop life support systems, and the challenges of living in confined, remote environments. In situ resource utilization, ISRU, is pivotal for the sustainability and success of human missions to Mars. By utilizing Martian resources, we can significantly reduce the cost and logistics of transporting materials from Earth, making prolonged stays and colonization more feasible. Extracting water from ice and permafrost. The most critical ISRU activity on Mars involves extracting water from subsurface ice and permafrost. Techniques such as drilling, heating, and sublimation can be employed to harvest this ice, producing drinkable water. Once extracted, the water must be purified for human consumption. This process involves filtration and sterilization to remove impurities and microorganisms. Oxygen generation. Electrolysis of water can produce oxygen, providing a renewable and efficient method for generating breathable air for astronauts. Hydrogen as fuel. The hydrogen produced from electrolysis can be used as fuel, potentially powering vehicles and equipment on Mars. Building materials. Martian regolith, soil, can be used to create building materials. Techniques like sintering, using heat to compact materials, or combining with binding agents can produce bricks or concrete-like materials for construction. 3D printing structures. Advances in 3D printing technology allow for the construction of habitats and other structures using Martian soil, reducing the need for prefabricated structures from Earth. Carbon dioxide processing. Mars' atmosphere, primarily composed of CO2, presents opportunities for resource utilization. CO2 can be processed to extract oxygen and carbon, which can be used for various chemical processes, including the production of methane fuel. MOXIE experiment. NASA's Perseverance rover's Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, is a pioneering effort to produce oxygen from Martian CO2, demonstrating the viability of atmospheric resource utilization. Solar energy. The most straightforward method for energy production on Mars is solar power. Solar panels can harness the sun's energy, though their efficiency can be affected by dust storms and the Martian day-night cycle. Nuclear power. For more consistent energy production, small modular nuclear reactors are being considered. These reactors can provide a steady power supply, critical for ISRU operations and human habitats. Growing food on Mars. ISRU also encompasses growing food on Mars. This involves using Martian water and regolith, potentially supplemented with Earth-sourced nutrients, to create a medium for plant growth in controlled environments. Life support systems. These agricultural systems can be integrated into life support systems, recycling air and water, and providing a renewable food source. Reliability and automation. ISRU technologies need to be highly reliable and capable of operating autonomously or with minimal human intervention, considering the communication delays and harsh Martian environment. Testing and development. Rigorous testing and development on Earth and in analogous environments like deserts or polar regions are crucial to ensure these technologies can withstand Martian conditions. Planetary protection. ISRU activities must consider planetary protection guidelines to avoid contamination of Mars with Earth-based organisms, which could compromise the search for Martian life. Sustainability. It is crucial to employ sustainable practices in ISRU to avoid depleting Martian resources or damaging the Martian environment. Global efforts. The development and implementation of ISRU technologies for Mars exploration will likely involve international collaboration, pooling expertise, resources, and funding from around the world. Continued exploration. Ongoing and future Mars missions will continue to focus on identifying and characterizing resources, particularly water, to inform ISRU strategies. Technology demonstrations. Future missions may include more technology demonstrations like MOXIE, testing ISRU concepts and technologies in the actual Martian environment. Extracting water on Mars is vital for the success of future human missions and potential colonization. However, this endeavor presents unique challenges and opportunities, given the planet's harsh environment and our current technological capabilities. Locating subsurface ice. The primary challenge is locating accessible subsurface ice. Radar data from orbiters like MRO has been instrumental, but ground verification is needed. Analyzing soil moisture content. Rovers and landers can analyze soil for moisture content. but deeper drilling is required to access substantial ice deposits. Drilling technology. Developing robust drilling technology that can operate in extreme Martian conditions, low pressure, temperature extremes, and dust storms, is a major challenge. Energy requirements. The energy required for drilling, heating, and extracting water is significant. Power sources need to be efficient and reliable, with solar and nuclear power as primary options. Water purification. Extracted water will likely contain impurities and perchlorates, necessitating advanced purification systems. Dust and weather. Martian dust can impair machinery and solar panels, while unpredictable weather and temperature shifts pose additional challenges. Transport and deployment. Getting heavy drilling equipment and extraction machinery to Mars poses logistical challenges in terms of rocket payload capacities and safe landing strategies. Advancements in drilling technology. Innovations in lightweight, energy-efficient drilling technology, possibly tested in extreme Earth environments, are essential. Use of local materials. Utilizing Martian materials for construction and machinery support, for example 3D printing with regolith, can reduce the need to transport materials from Earth. Autonomous operations. Given the communication delay with Earth, autonomous or semi-autonomous systems for water extraction and processing are necessary. Fuel and oxygen. Production. Extracted water is not just for consumption. It's a resource for producing oxygen and hydrogen, which can be used for breathing, fuel, and other chemical processes. Sustainability. Efficient use of local water resources is crucial for sustainable long-term human presence on Mars, reducing dependence on Earth-supplied resources. Understanding Martian geology and climate. The process of water extraction will yield valuable data on Martian geology and past climate, providing insights into the planet's history and evolution. Search for life. Drilling into the subsurface in the search for water may also reveal signs of past or present microbial life, if it ever existed on Mars. Planetary protection. There's a need to balance water extraction activities with planetary protection protocols to avoid potential contamination of Mars with Earth-origin microbes. Resource management. Establishing guidelines for the responsible and equitable use of Martian resources is essential, considering future missions from multiple countries and private entities. International cooperation. Collaborative efforts in technology development, shared data, and agreed protocols for resource use can maximize the benefits of Martian water extraction. Public-private partnerships. Partnerships between space agencies and private companies can accelerate technology development and deployment. Continued orbital and surface reconnaissance. Ongoing and future missions should continue to map and characterize potential water sources to inform extraction strategies. Technology demonstrations. Testing water extraction and purification technologies on Mars, possibly through dedicated missions, is a necessary step. The exploration of water on Mars is a central theme in current space research. Various missions, both operational and in development, aim to unravel the secrets of water on the Red Planet, from its historical presence to its current state and potential for future use. High-resolution imaging. MRO continues to provide high-resolution images of the Martian surface, helping to identify features related to water, like ancient riverbeds and lake basins. Radar observations. Its radar instruments, like SHARAD, shallow radar, probe beneath the Martian surface, searching for subsurface water and ice. Geological and atmospheric analysis. These rovers are analyzing rock formations, soil, and atmospheric conditions to gather data on Mars' past environment, including the presence and role of water. Sample collection. Perseverance, in particular, is collecting rock and soil samples, including those from ancient lake beds, which may contain clues about the history of water on Mars. Atmospheric studies. This mission is focused on analyzing Mars's atmosphere, specifically searching for gases related to biological or geological activity, including water vapor. Seismological research. While primarily focused on studying Mars's interior, InSight's findings also contribute to our understanding of the planet's geologic history, including the role of water in shaping its landscape. Subsurface ice mapping. Jointly proposed by NASA, ESA, JAXA, and CSA, this mission aims to map and characterize subsurface ice deposits, crucial for future human exploration. Sample analysis. In collaboration between NASA and ESA, this ambitious mission aims to return samples collected by Perseverance to Earth, where they can be analyzed for signs of past life and water-related minerals. Mineralogical studies. Rovers and orbiters are identifying hydrated minerals, providing insights into the historical presence of water and its interaction with the Martian crust. Data analysis. Advanced AI and machine learning algorithms are increasingly used to analyze vast amounts of data from Mars missions, helping to identify patterns and features related to water. Laboratory analysis. Scientists continue to study meteorites from Mars found on Earth, which can contain minerals and compounds formed in the presence of water, offering clues about Mars's aqueous history. Resource identification. Future missions will focus on identifying and assessing water resources in preparation for human exploration, including testing ISRU technologies. Remote sensing limitations. The interpretation of remote sensing data can be challenging, requiring corroborative evidence from multiple sources and methods. Environmental extremes. Mars' harsh environment poses significant challenges for mission longevity and data collection, particularly for surface missions. Global cooperation. The study of Martian water is a collaborative effort involving space agencies, research institutions, and universities worldwide. This collaboration is essential for pooling resources, expertise, and data. Integrated approach. A comprehensive understanding of Martian water will come from an integrated approach, combining observations from multiple missions with advanced modeling and laboratory studies. Mars orbiters play a crucial role in the exploration of the red planet, serving as our eyes in the Martian sky. Equipped with a suite of scientific instruments, these spacecraft provide valuable data and insights into Mars's geology, climate, and history, with a specific focus on the presence and dynamics of water. High-resolution imaging. MRO's HiRISE camera captures stunning high-resolution images of the Martian surface. These images have revealed intricate details of features related to water, such as river valleys, deltas, and gullies. Radar soundings. MRO's SHARED instrument uses radar waves to probe beneath the Martian surface, unveiling the presence of vast subsurface ice deposits. Neutron spectrometer. Mars Odyssey's neutron spectrometer measures the abundance of hydrogen below the surface, which is a strong indicator of the presence of water ice. MARSIS radar. The Mars Advanced Radar for Subsurface and Ionosphere Sounding, MARSIS on Mars Express, has detected subsurface water ice in the planet's polar regions. Atmospheric studies. While MAVEN primarily studies Mars's atmosphere, it provides insights into the escape of water molecules into space, helping us understand the long-term loss of Martian water. Spectral analysis. Many orbiters are equipped with spectrometers that analyze the reflected sunlight from the Martian surface. By examining the spectra, scientists can identify minerals and hydrated compounds, providing clues about past and present water interactions. Recurring slope lineae, RSL. Mars orbiters have observed intriguing features called RSL on Martian slopes. These seasonal dark streaks are believed to be formed by the transient flow of briny water. Safe landing sites. Orbiters provide crucial data for selecting safe landing sites for rovers and landers, taking into account factors like water availability and terrain. Global water mapping. Mars orbiters systematically map the distribution of water ice, providing a global perspective on its presence and concentration. Mineralogical characterization. Spectral data from orbiters help identify and map hydrated minerals, shedding light on the history of water on Mars. Data sharing. Scientists worldwide collaborate on the analysis of data from Mars orbiters, promoting a global effort to understand Martian water. Upcoming missions. Planned missions like NASA's Mars Ice Mapper will continue to enhance our understanding of Martian water by focusing on subsurface ice mapping. Resource management. Orbiters have limited fuel and lifetimes, requiring careful resource management to maximize their scientific output. Communication delay. The significant communication delay with Earth necessitates autonomous or semi-autonomous operations. The exploration of Mars and the quest to understand its water history is a truly global endeavor. Space agencies, research institutions, and scientists from around the world have come together to pool resources, expertise, and data in the pursuit of unraveling the secrets of Martian water. NASA, United States, As a pioneer in Mars exploration, NASA has launched numerous missions to study Martian water, including the Mars Rovers and Orbiters. ESA, European Space Agency. ESA has contributed to Mars exploration with missions like Mars Express, ExoMars, and collaboration on the upcoming Mars Sample Return mission. Roscosmos, Russia. Russia's involvement in Mars missions like the joint Phobos Grunt mission with China has added to our understanding of Martian water. ISRO, India. India's Mars Orbiter mission, or Mangalyaan, provided valuable data on Martian water and atmosphere. NASA's Rovers. While NASA's Mars rovers are primarily American, they have hosted international instruments and experiments. Scientists from various countries analyze data from these rovers. International instrument contributions. Instruments from countries like Spain, France, and Germany have been part of Mars rover missions, contributing to water-related research. Open access data. Mars orbiters, including NASA's MRO and ESA's Mars Express, provide open access to data. Scientists worldwide use this data for water-related research. Global data repositories. International space agencies maintain global data repositories where scientists can access and share Mars data, fostering collaboration. NASA-ESA collaboration. The Mars Sample Return mission is a joint effort between NASA and ESA. It aims to return Martian soil and rock samples to Earth, where international teams will analyze them for signs of water and life. International scientific teams. Scientists from different countries form collaborative teams to study Martian water, bringing diverse perspectives and expertise to the research. Laboratory studies. International researchers conduct laboratory experiments using Martian analog materials, sharing results to advance our understanding of water on Mars. Engaging the public. Collaborative educational and outreach initiatives aim to engage the global public in Mars exploration, fostering interest and support for these missions. Resource sharing. Collaboration allows space agencies to share the costs of missions and access each other's spacecraft and data. Diverse expertise. Collaboration brings together scientists with diverse expertise, enriching the quality of research and problem solving. Shared risk. Mars missions are risky, and collaboration can mitigate the financial and scientific risks associated with these endeavors. International perspective. Collaborative research offers a broader international perspective on Mars, ensuring a holistic understanding of Martian water. Mars, the enigmatic red planet, has captivated humanity's imagination for centuries. Among its many mysteries, the history of water on Mars stands as a profound enigma, one that has compelled scientists, space agencies, and researchers from around the world to embark on a collective journey of discovery. In this script, we embarked on a comprehensive exploration of Mars' watery past and the ongoing quest to unlock its secrets. We delved into the intriguing evidence of water's historical presence on the planet, from ancient river valleys and lake beds to the enduring polar ice caps and permafrost. The geological features that bear witness to past water flow, the sedimentary rocks that tell tales of Martian history, and the mysteries of the planet's polar regions have all been unveiled. We ventured into the realm of theories that seek to explain the loss of water on Mars, from atmospheric escape to the role of low gravity and the absence of a magnetic field. We discussed the complex interplay of climate change, the transition from a warm, wet climate to a cold, arid one, and the impact of axial tilt and orbital variations on Martian water dynamics. Exploring the current state of water on Mars, we discovered residual ice and frost, subsurface water, and the latest findings from Mars rovers, which continue to unravel the planet's aqueous history. The prospects for in-situ resource utilization, ISRU, offered a glimpse into how future human missions might harness Martian water for survival and exploration. We celebrated the collaborative efforts of space agencies worldwide, emphasizing the unity of purpose that drives the quest to understand Martian water. From NASA and ESA to Roscosmos and ISRO, international cooperation has enriched our knowledge of Mars and paved the way for ambitious missions like Mars Sample Return. Mars bears historical evidence of water, including ancient river valleys, lake beds, and erosional features. Geological formations suggest that liquid water once flowed on the planet's surface. Mars' ancient history reveals a warmer and wetter climate conducive to liquid water. Hydrated minerals and sedimentary rocks provide clues to past water interactions. Martian surface features like channels, deltas, and alluvial fans indicate the presence of flowing water in the past. These features suggest that Mars had a complex hydrological system. Sedimentary rocks on Mars, including those in Gale Crater, suggest the presence of ancient lakes and rivers. Exploration by rovers like Curiosity has uncovered evidence of water-deposited rocks. Mars has polar ice caps composed of water and carbon dioxide. Permafrost, rich in water ice, exists beneath the Martian surface. Multiple theories attempt to explain the loss of water on Mars, including atmospheric escape, low gravity, and the absence of a magnetic field. Climate change and orbital variations also played a role in water loss. Residual ice and frost are found on the surface, especially in the polar regions. Subsurface water exists, detected by instruments like radar and neutron spectrometers. ISRU technologies offer the potential to extract and utilize Martian water for human missions. Water can be used for drinking, oxygen generation, and fuel production. A variety of orbiters, rovers, and missions are actively exploring Martian water, providing valuable data. Future missions like Mars Sample Return will further our understanding. International collaboration among space agencies and research institutions drives progress in Mars exploration. Collaborative research projects and data sharing enhance our collective knowledge. Mars Aqueous History. Our exploration of Mars has revealed compelling evidence of a watery past, with signs of ancient river valleys, lake beds, and sedimentary rocks. This implies that Mars once had a more hospitable climate, potentially suitable for life as we know it. Understanding this history contributes to our broader understanding of planetary evolution. Water as a resource. Water is a critical resource for future human missions to Mars. Our knowledge of past and present water on the planet is essential for planning and sustaining long-duration missions. It provides a potential source of drinking water, oxygen production, and hydrogen for fuel, reducing the need to transport these resources from Earth. Mars climate dynamics. The study of Martian water loss due to factors like atmospheric escape and climate change informs our understanding of planetary climate dynamics. This knowledge is relevant not only to Mars, but also to the study of Earth's climate history. Collaborative research. The collaborative efforts among international space agencies and research institutions underscore the importance of global cooperation in space exploration. This collaborative model sets a precedent for future interplanetary missions and promotes the responsible use of space resources. Mars as a scientific laboratory. Mars serves as a natural laboratory for studying geological and climatic processes. By analyzing its features and history, we gain insights into Earth's own geological and climatic past, as well as potential scenarios for planetary evolution. Prospects for life. The presence of water, even in its frozen or subsurface form, raises questions about the potential habitability of Mars, past or present. While we have not yet found direct evidence of life, our understanding of water on Mars informs the search for microbial life in the future. Future human exploration. Our understanding of Martian water is instrumental in preparing for future human missions to the planet. It informs the development of technologies for water extraction and purification, resource management, and mission planning. Sustainability and resource utilization. Sustainable exploration of Mars relies on efficiently utilizing local resources like water. By harnessing Martian water, future missions can reduce their reliance on Earth-supplied resources, making exploration more feasible. Search for life. One of the most tantalizing possibilities is the discovery of past or present microbial life on Mars. Future missions, such as the Mars Sample Return mission, will bring back samples from the Martian surface, offering the opportunity to search for signs of life in Earth-based laboratories. Subsurface exploration. The subsurface of Mars remains relatively unexplored. Future missions may include drills and landers designed to penetrate deeper into the Martian crust, potentially uncovering preserved evidence of water and life. Improved instruments. Advances in instrumentation, including more advanced spectrometers and detectors, will enhance our ability to analyze Martian samples and remotely study the planet's surface and atmosphere. Sample analysis. The analysis of samples returned from Mars has the potential to revolutionize our understanding of the planet. The Mars Sample Return mission will provide scientists with pristine Martian material to study. Advanced rovers. The next generation of Mars rovers may be equipped with more advanced mobility, autonomy, and scientific instruments, allowing for more extensive and targeted exploration. Human missions. As human missions to Mars become a reality, there will be a wealth of opportunities for on-site exploration and research. Humans can conduct experiments, gather samples, and make real-time observations. International collaboration. Collaboration between space agencies and countries will continue to play a crucial role in advancing Mars exploration. Shared resources, expertise, and data will drive progress. Resource utilization. The development of technologies for in-situ resource utilization, ISRU, will enable the efficient extraction and use of Martian resources, including water, for sustaining human presence on Mars. Climate and environmental studies. Ongoing atmospheric and climate studies will help us better understand the current Martian environment and its potential for human habitation. Spacecraft and orbital missions. Ongoing and planned orbital missions will continue to provide high-resolution imagery and data about Mars, contributing to our understanding of its geology, weather, and water dynamics. Private sector involvement. Private companies are increasingly becoming involved in Mars exploration, bringing innovation and competition to the field. Commercial ventures may open new avenues for research and resource utilization. Education and outreach. Mars exploration captures the public's imagination. Continued educational and outreach efforts will engage the next generation of scientists and explorers, fostering enthusiasm for space exploration.